Chapter 7, reproduction numbers continued. We have a column here with some basic reproduction numbers. I'll explain where these come from. And we saw last time if we take 1 minus 1 over the basic reproduction number, that gives us the fraction we need for immunity to have equilibrium. And then, of course, if we go a little bit beyond that, the virus will die out on its own. Reproduction number of 1.5, that's normal for a seasonal flu as it gets introduced to our population in the United States. If you take a 1 minus 1 over 1.5, we end up with 0.3333. So we need 33% or 1/3 immunity for the virus to reach equilibrium. A little bit beyond that, it will die out. And that's easily accomplished through a combination of vaccination and immunity because of exposure. We'll talk more about that in a minute. 2.0, now we need half the population to be immune. It becomes more difficult. 2.2, that was an early COVID number given last February 2020. We end up with 54.5%. And there are more recent studies. There are COVID numbers varying between mid-2s all the way up to 7. 7 in France, I think, is the highest number produced by a model. But if the basic reproduction number is 3, then suddenly we need 2/3 of the population to be immune. And that's very difficult. There have been some suggestions that we just open everything up, everybody catch the virus, we try to reach herd immunity through infection. And that would be very difficult. We would need 2/3 of the population to become infected, which would cause our hospital system to shut down. And beyond that, there's a possibility that after 9 months to a year, you may lose your immunity because there may be enough mutations, possibly, so that you may become reinfected, in which case we have to start that cycle over again. It's possible, there's still quite a bit of unknown about COVID, but it's quite possible that without a vaccination, the only way to defeat COVID would be to keep us perpetually sick, the majority of our population. So that's really an impossibility. It's just not going to happen. It's basic math. As far as the average reproduction number for COVID, there's a little bit of uncertainty here. When we build these models, there are multiple methods for producing a reproduction number for COVID. We'll talk about one at the end of this video series. But you can use stochastic methods, you can use Monte Carlo methods. They all produce slightly different figures. And of course, it varies from population to population. But I think one thing that's certain is COVID is a lot more serious than the seasonal flu. We know that. We don't know exactly where it lines up compared to that, but it's definitely more serious. No one ever measures the reproduction number of COVID to be anything close to this. So I think we have statistical certainty that it's quite a bit worse. And the percentage that we need for herd immunity is much, much, much greater and probably unmanageable by itself with just simple infection. 15.0, that's a median value for measles. Measles is 12 to 18, spreads seriously, seriously fast. You need 93% immunity. Which we have. When I was growing up, everybody had caught the measles that was over a certain age. Very rare to run into an adult that didn't have it. So it meandered through the youth population because we had pretty close to herd immunity. We reached the kind of an equilibrium point. Now through vaccination, kids don't have to have it, have to get the measles disease. So here's a plausible scenario with the common flu. Here's what happens. Common flu, R0 1.5. Vaccination, we can lower it. How much we lower it all depends on the how many people get the vaccine and also the effectiveness of the vaccine. Sometimes we miss the target because these things mutate, sometimes faster than others. So, but during a normal flu season, 1.5 may decrease to 1.1 for the effective reproduction number because we have some immunity. Uh, of course, it goes through the population. Maybe the infections lower it to 0.9. And then springtime comes in natural social distancing. We're outside. If we're outside, that slows down the spread of the disease. Maybe RE goes down to 0.7 or 0.5 and then it dies out. That's the normal progression. Uh, COVID, most states actually had an effective reproduction number this summer of 1.0, give or take a little bit. We reached equilibrium status. We weren't able to get it down significantly below 1 so it would die out. It was just impossible because we're starting with a higher number. If you start with a 3, guess what? You have to work a lot harder to get down here. Of course, we didn't have a vaccination, so all we had was infection and any kind of social distancing. So that's proof. I mean, the fact that it was measured in virtually every state at hovering around 1.0, that's proof that this is, or evidence that this is starting at a much higher number. So that's all. The couple of videos away, we're going to build the SIR model. And I built the SIR model to include this parameter. So I haven't seen this formulated this way anywhere else, but I built it with this parameter. That way you can vary this parameter and see what effect it has down the road. And you can see the seriousness of COVID and other viruses in terms of what's going to happen in the future, not just this aspect right here. So, okay, that's all for this video.